All right, well, hello everyone. Thank you for coming today. Also, thank you to ClueCon for giving us a platform where we can talk about our technologies and present throughout the week. All right, so my name is Jason Kraft. I'm a senior network engineer for Telnyx. My roles and responsibilities are network architecture and engineering. And we're going to be talking about the strategy and the technical details behind our global backbone. All right, so to get started, let's talk about the agenda for today, what we're going to talk about. Why build a network to begin with? So we'll go through some of the challenges that we've discovered and some of the things that we're trying to solve. We're going to go into some of the details about the IP backbone itself. We'll talk about how it works, the mechanisms that we're using to present our network to the internet in a way that's performant and has quality of service built in. And then we're going to talk about the cloud. So Telnyx is a cloud-centric organization. We're building in multi-clouds with a cloud-agnostic approach. And essentially, we're using that as a replacement of a traditional physical data center. So we'll dive into that a little bit later. And then we're going to talk about our routing and pairing strategy as it applies to internet connectivity. All right, so why build a network to begin with? Why is it necessary, and what are we hoping to solve by doing this? All right, so things that the internet are great for today, web browsing, websites, as much of everyone in here can probably see, getting connectivity to their sites for research, whatever it might be that you're doing to perform your jobs, non-RTC based applications, and things like cloud or content delivery networks for streaming of media, whether it be movies, music, various other applications and such. But we still, despite all the evolution over the last couple of decades of internet growth and capacity, we still find that it's rather difficult at times to apply QoS to RTC-based applications when you're building voice and video for the internet with service providers that really probably don't care about your traffic, or they don't care about applying the same quality that you would expect when they're servicing other customers. So Telnyx went down the path. We basically decided that we needed to build a network infrastructure in order to present our services, our product and platform to the outside world. So the network infrastructure was built with a design implication of increasing call quality and performance from end to end. And we're looking to attack certain key indicators such as latency, looking to lower latency from the customer to our network, looking to reduce jitter, and we're looking to get as close to 0% packet loss as absolutely possible. All right, so how were we doing this without the network? So being a cloud-centric organization, we landed ourselves in AWS, landed ourselves in Azure, and then we needed to have connectivity between those clouds, and we realized that the only way to actually accomplish this was to build a VPN tunnel between those between those environments. So then a third cloud came along, and then a fourth cloud came along, and now what you're talking about now is a highly unscalable full mesh of VPN tunnels. When the fifth cloud and the sixth cloud comes along, you're kind of left with a lot of this administrative overhead, a lot of network management that can quickly become very cumbersome to actually deal with. So the other aspect of this is if you're wanting to use your own IP space, let's say you want to get out there and register with Aaron and get your own public blocks and then apply them to the clouds themselves. Well, the clouds, typically their story is use our IP space, don't worry about your own. So we decided that to combat this project or combat this, being able to actually use our own IP space, a network infrastructure was needed. In addition, there's maybe some fancy things you can do on the host to handle QoS directly on each node. But for the most part, you're dealing with the best effort of each cloud and their representative service providers in the middle. Okay, so we've decided it's time to build a network. And we're looking at getting off the ground, so we're going to start with a single POP. And as an example, let's just say that this first POP starts in we start to build it in the East Coast of the US. So a lot of these customers that are in that particular area are going to say, great, your latency is low. We can reach your network. Very little packet loss. There's very few hops in between. And then when we look at customers that may be in remote areas, Midwest US, Western US, they're just by nature going to see a higher degree of latency than customers that we would have on that Eastern Coast POP. And in addition, just going through all these various service providers to actually get to us, they may or may not experience a degree of packet loss that's undesirable. But for the most part, it's pretty much out of their control in terms of what's happening at those service providers in the middle, the links that they're taking, and what measures are being taken to reduce packet loss, jitter, and latency. So then we're going into this multi-pop network model. So global IP backbone, multiple pops. And what we're looking basically to do here is have enough geographic coverage where we can have routing visibility to as many customers as possible, and essentially decrease the latency, decrease the idea that packet loss could be in the middle, and shorten the path between the customer network and the Telnyx network. So the idea here is that we're trying to shorten the cable, and that's a general theme that you're going to hear throughout this presentation, and as if you talk to any of my fellow Telnyx team members, is that shortening the path between the customer to our network is one of our common goals with actually having a network infrastructure. All right, so let's dive into a little bit of the IP backbone details. We're going to talk about how we're building this, what mechanisms we're using to actually get this all to work. So where to actually build the POPs. So we've talked about this network infrastructure. We've talked about using clouds. We've talked about having multiple POPs. We actually need a place to actually do this. So we're going to need space, we're going to need power, and we're going to need proximity to all of the major providers that we want to interconnect with. So today we're using Equinix to accomplish this. So we have Equinix data centers that are located in 3 major metros that we'll see here in a second. And what you're seeing here on the slide is a picture of a standard Telnyx POP. Now this actual rack of gear we just installed recently in a network refresh. And this is a standard model that we apply to every POP that we build. So be it in Chicago, could be in Washington, it could be in the Bay Area. This POP will always look the same given the constraints based on any of the POPs that we're building in. So the idea here is that we're going to be close to major ISPs that we want to interconnect with and all the cloud providers that we're going to be working with. So we're following the customers and we're following the peers. Essentially, again, shortening the path. So what is needed? We need all this network hardware, right? And what we like in our hardware and in our network of choice, we're a heavy BGP organization. So BGP is our primary routing protocol that we're using to actually announce routes, consume routes, and then pass that traffic across our backbone. We need the ability to do full tables, which gives us the highest degree of routing and visibility within each metro that we're located in. We also like to have Mpls capable switches, capable routers to be able to signal label switch paths so that we can do things like traffic engineering, layer 3 VPNs for customer dedicated environments, and so forth. We also like low latency gear, things that are programmatic that allow us to easily apply network automation into the environment. And we're also looking to obviously expand, so we like hardware that's going to be very easy to grow with capacity, and also apply QoS into the environment. So today our current POP locations, and I kind of briefly mentioned this earlier, our backbone right now is in the US, and we're located in the Washington, DC metro, in Ashburn, Virginia, that's where our POP is in DC, Chicago, and San Jose, covering the Bay Area out on the West Coast. And all of these locations have been chosen primarily because they're near the major internet hubs within the country, and they're also located near all of the cloud providers that we want to have direct cross connects with. Okay, so as we talk about further POPs that are in progress, that are basically in progress for expansion, our approach and our goals are to, by the end of 2017, to be in 15 to 20 locations around the world. And our first stab into this is to build out our London POP to have EMEA coverage. We're actually in a state of provisioning at this moment, and within the next 30 to 45 days, we'll be going live in that area. And then we're looking to wrap up the year covering Asia-Pac with our Hong Kong POP. So again, some of the key features that we're looking to build into the infrastructure, we're pairing with Tier 1 ISP transit providers. We're connecting to internet exchange points at each metro that we're located in. And we're also offering direct cross connects to third parties, customers, or anyone who has a good use case to actually be connected to our backbone. Again, BGP with full routing tables is important for us. We also have an Mpls signaled IP backbone that allows for things like layer 3 and layer 2 VPNs for dedicated customer environments or Telnyx environments themselves. And we have dedicated fiber paths between all of our POPs. In all cases, we have 2 paths that are diverse between providers. In some cases, we have 3. And this is basically building the IP backbone for transport between our POPs. And then, of course, the end-to-end QoS and prioritization of voice and video traffic using Mpls traffic engineering and RSVP. So let's go into a little bit of routing the backbone. So again, BGP is our primary routing protocol. It's very heavily used in our environment. We're only using this routing protocol to actually announce routes across the backbone, but also to connect to major ISPs, as it's a standard protocol for all internet traffic today. So iBGP and internal BGP setup for us is that each POP is paired with each other, announcing the routes that they've learned from the network edge, from all the IXs, all of the transit peers that we're connected to. And then in addition, BGP being a very highly scalable protocol with multiple address families, we're able to route IPv4 traffic, v6, and also traffic such as layer 3 VPNs, layer 2 VPNs. Okay, so how are we actually announcing these routes out to the outside world? So at each major metro, we're looking at an edge, core, and interconnection layer. So at the network edge, we're essentially announcing to the world a major block of address space. So this major block of address space tells the rest of the internet, hey, come to me, and if you want to connect to Telnyx, okay? From that point, the core is where all the routes are actually originated from in each metro that we're located in. So what you're going to see here momentarily is that if you're trying to connect to Telnyx and you're located in San Francisco, then you're going to arrive in San Jose. If you're in New York City, you're going to arrive in Ashburn and so forth. So all of our public routes are originated from the core, they're announced across the backbone, and then the edge takes care of announcing those out to the rest of the internet. So what you arrive at with this multi-POP global IP backbone model is that the customer's network now is as close as possible to the Telnyx network if they're using IP transit or ISP space to actually reach us. As you'll see in a little bit, there's some other options that are available to actually shorten that path even further, but the whole point here is to actually reduce the amount of time it takes for someone to connect to us. And to go through a couple of examples here. So we've used a public available looking glass with Cogent's network to actually run some trace routes to present here. And what you're seeing is a trace route within the Washington, D.C. area that originates in the Cogent network. It transits through NTT, who we're using for Tier 1 transit service in Ashburn. And then it ultimately arrives in our network here at the 6th and 7th hop. Okay? Likewise, if you look at a trace route from the Bay Area, so this trace route, again, is originating from Cogent. It's traversing Cogent through NTT's network and arriving at our network at hop 6 and 7. So this is all transit traffic, and one of the cool aspects of the environment when we talk about direct interconnection is reducing all of the service providers in between as much as possible. So this is a trace route from a Comcast customer that is it's coming from their on-prem network, and it's essentially riding through Comcast network and arriving at hops 9 and 10, which are the Telnyx network at 350 Cermak just down the road here in Chicago. So all of this traffic on this particular trace only exists in the Comcast network, so it went from the customer's network through Comcast and hit Telnyx at our edge. And then from there, all the packets begin to route within our internal backbone, which we'll see what happens on this next slide, what we're dealing with for packets that are ingressing into the network and packets that originate within the network. So we're using Mpls traffic engineering and RSVP and a number of other QoS mechanisms to mark and identify traffic that is voice-related, video-related, SIP, RTP, things of that nature. And basically a flag is marked on each packet, and as it traverses the network, it's told at each hop which path to actually take. So if any of this traffic, say, for example, begins in the West Coast and its ultimate destination is somewhere out east, it's going to be told by the network, use what we consider like our A-side QoS path. So the A-side QoS path is only going to hold voice and video traffic only. It's typically a path that's the lowest latent path that we have at our disposal. So for example, like a path from San Jose to Ashburn would ride a link that's 66 milliseconds in round trip time. versus some of our best effort B-side paths, which can get up into 76 and the high 70s, depending on the providers that we're using. But essentially what we're trying to do here is say that anything that's voice or video related is going to be treated with a higher degree of prioritization, and it's going to use paths that are dedicated only for that. So any of the other leftover traffic that's in the environment, all packets that are HTTP in nature, maybe database transactions in nature, are going to take a B-side best effort path. They'll still arrive at the destination, but they're not going to compete with any of the voice stuff. And all of this is essentially accomplished using Mpls TE, which we signal across our backbone. All of the core nodes are capable of forming label switch paths from end to end, and then with the markings, with the QoS configurations, we're able to actually apply this prioritization. And so what happens if the A side fails? Then the A side just reconverges immediately over to the B side using various fast reroute mechanisms, such as like BFD or the protocols themselves with fast reroute capabilities built within them. So the packet loss on a failure rate, depending on where it's at in the network, can be as little, it's pretty much sub-second at this point. So what happens now is that the voice traffic is on that B-side path, but it's still marked with the same configuration that we talked about earlier, and it's treated with a higher degree of priority on that B-side path as well. Okay, so let's get into the cloud for a little bit. So the cloud, again, we're utilizing as our data center. So Telnyx is not building rows and rows of cabinets of servers and bare metal hardware. We're essentially building one single rack of gear in each of our metros and each data center that we're located in. And that network hardware is then cross-connected with cloud service providers and also the internet service providers that we want to connect with. And essentially, we come up with a picture like this, where we have direct fiber access into each cloud. So we're using AWS, we're using Azure, we're using SoftLayer, Google. And all of these links are then connected back into our interconnection layer gear. From that perspective, the interconnection layer is, again, doing this the cross-connection with the clouds. And we're doing BGP over those connections to announce virtual networks that we create in each cloud. So all 4 of the clouds on one side and all 4 of the clouds on the other side are being built with Telnyx private IP space. And then we announce that back in to the network core using the interconnection layer. The core then announces those routes across the backbone, and what you have is a fully converged IP backbone where a node in AWS can reach a node in Azure in completely different areas of the country, all riding our IP backbone transport paths. Okay, so all this stuff is great. We have clouds, we have interconnection, we have cross-connects and connectivity to major service providers, major cloud providers. We have our own backbone. So how do we actually get these instances to talk to the outside world when they were likely meant to only use the IP space of the cloud provider in question? So what we're actually doing there is we're announcing a default route into the cloud. So for example, our virtual network or our VPC in Amazon receives a default route from our, in this case, interconnection layer that was originated from the core. And so it tells that virtual network, all of your default traffic route back to Telnyx or route back to our backbone. So with the model in place, all of that traffic eventually ends up into the core of the metro that we're working in, or at least this particular cloud is connected to. And then we're natting all of this IP, all of these instances at the actual core. So every metro, every POP that we build, and every cloud that we build has a dedicated block of public IP space. And within that block, we take specific IP addresses, and then we map those to internal addresses of each cloud that need to be exposed to the outside world. So that's how we're handling actually getting traffic from the cloud through our backbone and then presented to the world using our own IP space versus the clouds. Okay, so we can talk a little bit about the routing and peering strategy, and some of this we've already kind of touched base on, but we'll go over it at a high level here. So routing on the internet in general, like I mentioned earlier, we're using tier 1 transit providers. So essentially this is another mechanism that we're using to actually shorten the path between the customer network and the Telnyx network. Some of our customers may come in on a tier 2 or a tier 3 transit. They may also actually be on a tier 1 transit, but ultimately they're going to find their way to the Telnyx network by traversing through tier 1 transit providers that actually only peer with each other. So other routing and peering strategies that we have at our disposal, we talked about IXs earlier, so internet exchange points. So essentially these are switching fabrics or some type of fabric located within the typically within the building or the data center ecosystem of the metros that we're located in. There's many IXs. We're positioned on a few within the metros that we're located in. And essentially what this is a place where people can directly cross-connect to the IX, become a member, and then say, hey, I would like to peer with you over the IX. I don't want to send all of my traffic out to the internet just to reach you. I would like to go directly if we can. So this is another mechanism of being able to do that. So you can peer up with organizations like a Netflix, a Google, Amazon, or you can actually peer with customers over that. So if a customer of Telnyx wants to actually peer directly over the IX, that capability exists. And then lastly, if the use case presents itself, we can do direct cross connects. So we kind of talked about this with Comcast, right? We'll be able to, essentially what this means is that you can run a direct cross connect from your gear to ours. We can turn up configuration on that cross connect, peer with each other, and then announce each other's routes into each other's networks. So again, we're shortening the cable. We're getting as close to the customers as possible. It would be great if we could do this with all customers, but we still need the internet in order to route traffic when these mechanisms are not available for everyone. So kind of to summarize what we talked about, again, the general theme here, we're trying to shorten the cable. We're trying to get as close to our customers as possible to maintain a sense of quality and deliver the best possible performance that we can within our infrastructure. Cloud-centric uptime and is given through geographic diversity, redundancy, resiliency. So all of this has been purposely built in order to maximize quality of service within our own environment in such a way where we can announce to the outside world, announce to the general internet, bring customers as close as possible to us, and then also offer capabilities to do things a little more direct if necessary, and thus shortening the cable even further. That kind of wraps up everything on the presentation. Is there any questions? Yes. So on like the hardware itself? Yeah, so both at all layers there are multiple devices. So at the edge there's 2 edge routers. At the core there's 2 core routers. Interconnection also has 2. So basically any piece of hardware that we deploy that's considered production traffic will have a neighbor of sorts built in with it.
You want to go run, Mike?
Mm-hmm. Are you talking about latency like end-to-end, like round-trip times? So typically that can come with the negotiation up front when you're talking about SLAs with those carriers. A lot of times they'll have different levels of, hey, we have a fast path, we have a B-side path, maybe we just have a general best effort path between the POPs in question. So we just, nearly all the time what we're trying to do is find something that's, that's cost-effective that also has a low round-trip time. That would probably be correct, yes. Yep. We can talk about this more offline if you like to. Okay.
One question back here.
Yep.
Your clients are, what kind of clients do you serve? Like mobile phones, PCs? What are your clients? Regular phones?
Yeah, so today we're looking at clients that would have like maybe a cloud PBX, call centers that would be wanting to connect to us. Anything that would, any customers that would be looking to connect to our SIP telephony engine.
So in terms of latency, do you have any data in terms of comparing latency between the coasts, right? So for example, if you did not have your Bay Area center,
right,
and two of your customers in San Jose are talking to each other through Virginia,
yep,
versus them talking through your San Jose center, do you have a sense of what the additional latency is?
Yeah, I actually have some numbers actually on my laptop. If you want to hook up after I get off stage here, we can kind of go through some of the figures that I have.
All right, wonderful. Big round of applause.
Thank you, everyone.